You know, usually when we talk about generating power, whether you are just trying to, like, boil a pot of water or literally light up an entire city, there is this fundamental expectation of, well, destruction.
Right. Yeah.
Like, think about a campfire, right? You take a piece of matter, a log, you add heat, and it just breaks apart chemically. It gives off warmth, but it is entirely about tearing things down.
Exactly. It's a chemical breakdown. We are basically severing bonds to release the energy that's stored inside them.
Right. You burn coal,
Mhm.
you ignite natural gas, or, I mean, even if we look at traditional nuclear power, you take a massive, unstable atom like uranium, and you violently split it in half.
Yeah. Fission.
Fission, exactly.
Mm.
It is always about breaking things apart to get the energy out.
And I mean, that makes intuitive sense to us, right? We understand breaking things. It feels very terrestrial, very much aligned with our day-to-day experience of the physical world.
Yeah, it does. But then, you step into the world of nuclear fusion, and suddenly that campfire metaphor is just turned completely upside down.
Oh, completely.
We're looking at a physical landscape that isn't about destroying matter to harvest energy. It's about, like, forcing things together.
It is the absolute definition of bottling a star. I mean, you are no longer dismantling the universe at that point. You are actively forging it.
Welcome to the deep dive. I'm just so thrilled you are here with us today because as I was pouring through the massive stack of research compiled for our discussion, specifically, we're drawing from the incredibly comprehensive Wikipedia article on nuclear fusion and, a whole host of supporting historical and physics notes. And I just kept getting stuck on this one idea.
It's a big one.
We are literally trying to replicate the ultimate power source of the cosmos right here on Earth. So our mission today is to entirely demystify this process for you.
It's quite a journey.
It really is. We're going to journey from the unimaginably hot core of our sun into the top secret, highly dangerous Cold War tests in the Pacific and all the way to massive, cutting-edge laser facilities in California. We're going to figure out why bottling a star is both our greatest engineering challenge and quite possibly the most incredible hope we have for the future.
It really is an unparalleled scientific saga.
Yeah.
Because the fundamental premise of fusion is deceptively simple to state, right? But it's agonizingly difficult to actually achieve.
Right.
You are taking two atomic nuclei and you are smashing them together so hard with such overwhelming energy that they overcome their natural desire to repel one another.
Like two magnets.
Exactly. And they become one single heavier nucleus. And in that union, they release a just staggering amount of energy.
Which, sounds simple, like mashing two pieces of clay together until you actually try to do it with the fundamental building blocks of reality. So, okay, let's unpack this.
Let's do it.
Before we can even talk about how to build a reactor with giant magnetic donuts or arrays of super lasers, we really have to understand the fundamental physics of the cosmic engine. Like, why does smashing two things together make energy in the first place?
Yeah.
And why does the universe make it so insanely difficult for us to do it on purpose?
Well, to understand the why, we have to zoom way, way in. We have to look at the two fundamental forces doing battle inside the nucleus of an atom.
Okay.
First, you have the Coulomb force. This is the electrostatic repulsion between positively charged particles.
Right.
Inside a nucleus, you have protons, which carry a positive charge, and neutrons, which carry no charge. So if you bring two protons close together, they violently want to push apart.
Right. I always think of this like trying to push the north poles of two insanely powerful neodymium magnets together.
That's a great way to picture it.
When they are far apart, you don't feel much.
Yeah.
But the closer they get, the harder they push back. And it's not a linear push, right? The closer you try to force them, the resistance just goes up exponentially.
Precisely. That invisible wall of exponential repulsion is called the Coulomb barrier. The closer they get, the more energy it takes to push them that final fraction of a millimeter.
Okay.
But, and this is the key, if you can somehow push those protons incredibly close together, and we are talking about distances on the scale of a femtometer.
Wait, a femtometer? How small is that?
It's 1/1,000,000th of a billionth of a meter.
Oh, wow.
Okay, it's unimaginably small, but if you get them that close, something magical happens. Another force abruptly takes over. This is the strong nuclear force.
The superglue of the universe.
That is exactly it. The perfect analogy. The strong nuclear force is immensely powerful. It's exponentially stronger than the Coulomb force that is trying to push the protons apart.
Okay.
But it has a phenomenally short range. It essentially only works if the particles are practically touching. So the entire game of nuclear fusion, the whole billion-dollar endeavor, is finding a way to push those North Pole magnets close enough together for the superglue to suddenly catch and snap them into one piece before they can fly apart.
Okay, I follow that. They snap together, the superglue catches.
Right.
But where does the actual energy come from? Because if I go back to my clay analogy, if I take 2 one-pound lumps of clay and smash them together, I just have a 2-pound lump of clay.
Right.
It doesn't, like, explode and power my house for a year.
No, it doesn't. And this is where we have to totally discard our everyday understanding of mass and bring Albert Einstein into the conversation.
Ah, E equals mc squared.
Exactly. His theory of mass-energy equivalence. Energy equals mass times the speed of light squared. When you take light nuclei, specifically elements lighter than iron, and you fuse them together, the new nucleus you create is actually slightly lighter than the sum of the individual parts that went into it.
Wait, pause. The math literally doesn't add up. You're saying 1 + 1 equals, like, 1.99?
That is exactly what I'm saying. A tiny fraction of the mass, it's about 0.7% of the total mass of the protons and neutrons, simply disappears from the physical universe as matter.
That is so weird.
It is. But it doesn't just vanish into nothingness. It is converted entirely into pure energy. And because the c² in Einstein's equation represents the speed of light multiplied by itself, which is a mind-bogglingly massive number, that tiny missing fraction of mass translates to a colossal amount of energy.
Just to help me conceptualize this, because I need a visual. How much energy are we talking about from a tiny amount of mass?
Well, to give you a sense of scale, if you could completely convert just 1 single gram of matter, so about the weight of a standard paperclip, entirely into energy, it would yield about 9 × 10⁻13 joules.
Okay, yeah, I'm going to need you to translate joules into something my brain can actually picture, because times 10 to the 13th just sounds like math homework.
Fair enough. The energy released by completely converting a paperclip's worth of mass into pure energy is roughly equivalent to the energy released by detonating 21 kilotons of TNT.
What?
Yeah, that is significantly more powerful than the atomic bomb dropped on Hiroshima, which was about 15 kilotons, all from 1 gram of matter.
That is absolutely mind-bending. A paperclip.
It's just a paperclip.
And fusion is tapping into that exact mechanism, just shaving off tiny fractions of a percent of mass every time 2 atoms stick together.
Exactly.
But wait, you mentioned a very specific caveat a moment ago.
Yeah.
You said this works for elements lighter than iron. Why iron? Like, what makes iron so special in the universe?
That is known in astrophysics as the iron limit. It has to do with something called the nuclear binding energy curve.
Okay.
As you fuse very light elements, like hydrogen into helium or helium into carbon, the resulting nucleus is more tightly bound, and you release energy in the process. You get a massive return on your investment.
Right.
But as you move up the periodic table, the returns diminish. Iron, specifically the isotope iron-56, sits at the absolute peak of this curve. It has one of the most tightly bound, stable nuclei in the entire universe.
So it's like the bottom of the hill. The ball just can't roll any further down.
Exactly. Because it is so stable, if you try to fuse iron with anything else, say smashing 2 iron atoms together, or smashing an iron atom with a helium atom, it doesn't release energy. It actually absorbs it. The reaction becomes endothermic.
Oh. So iron is basically the ash of the stellar fire.
It is the ultimate cosmic ash. And this specific fact of physics is exactly why massive stars die.
Really?
Yeah. For millions of years, a giant star lives in a state of equilibrium. It is fusing lighter elements in its core, releasing immense outward energy, and that outward pressure pushes against the crushing inward force of the star's own gravity.
Like a giant tug-of-war. Gravity pulls in, fusion pushes out.
Yes. But eventually the star fuses heavier and heavier elements until its core turns to iron. The moment the star tries to fuse that iron, the fusion reaction suddenly starts sucking up energy instead of producing it.
Oh.
So the outward pressure instantaneously vanishes. Gravity wins the tug-of-war without contest. The entire mass of the star collapses inward at a significant fraction of the speed of light, hits the dense iron core, rebounds, and blows the star apart in a supernova.
Incredible. And it all comes down to the microscopic behavior of iron atoms.
Mm-hmm.
So obviously, if we want to build a reactor on Earth, we clearly want to stay far, far away from iron. We want the light stuff that's up the top of the hill, hydrogen. Helium.
Precisely. And helium-4, which consists of 2 protons and 2 neutrons, is the absolute golden child of this entire process. It is exceptionally stable. In the terminology of nuclear physics, we call helium-4 a doubly magic nucleus.
Doubly magic. That sounds like something out of a fantasy novel, not a physics textbook. What does that actually mean?
It refers to quantum mechanics. So just like electrons have shells around the nucleus that they want to fill up, the protons and neutrons inside the nucleus have energy shells too. When a nucleus has a magic number of protons or neutrons, those shells are completely full, making the nucleus incredibly stable and just completely unwilling to break apart. Helium-4 has a magic number of protons, which is 2, and a magic number of neutrons, also 2. Hence, doubly magic.
I see.
It drops into its lowest quantum energy state. Because it is so stable, creating it releases the maximum possible amount of energy. It is the ultimate, highly desirable byproduct of fusion.
Okay, so we know our target. We need to smash the lightest stuff hydrogen together to make this doubly magic helium, and we have to push hard enough to overcome that crazy magnetic repulsion, that Coulomb barrier.
Yes.
If I'm an engineer trying to build this, how much actual heat, how much temperature does it take to push those protons that fast?
Well, this is where we run into a major historical roadblock. Physicists use a unit called an electron volt, or EV, to measure the energy of these particles. And MeV is 1,000,000 electron volts. The Coulomb barrier between 2 protons is about 0.1 MeV. If we use standard classical physics like, calculating the speed of 2 cars crashing to give protons enough kinetic energy to overcome a 0.1 MeV barrier, you would need to heat the hydrogen fuel to roughly 1.2 billion Kelvin.
1.2 billion degrees. I mean, if you're listening to this and trying to picture 1.2 billion degrees, don't worry, your brain isn't built to comprehend that, neither is mine. I read that the center of a nuclear bomb explosion is around 100 million degrees, so we need it to be 12 times hotter than a nuclear weapon.
Right. And here is the great temperature paradox that completely baffled earlier 20th century physicists.
Well, this is the part I love.
We know through observation and deduction that fusion is happening right now in the core of our sun. But we also know the mass and pressure of the sun, and we can calculate that the core of the sun is only about 13 million Kelvin.
Wait a second. 14 million is way, way less than 1.2 billion. It's not even close.
Ain't at all.
How is the sun fusing anything if it's almost 100 times too cold to get over the Coulomb barrier? By classical physics, the sun should be a dark, cold ball of gas.
It absolutely should be. And this paradox wasn't solved until 1927, when a physicist named Friedrich Hund discovered a deeply weird phenomenon called quantum tunneling.
Quantum tunneling, okay.
You see, in the quantum realm, particles like protons do not act like solid billiard balls. They don't have hard edges. They act like waves of probability. The exact location of a proton at any given microsecond is not a fixed point. It is smeared out across space.
Okay, my brain is starting to hurt a little bit, but stay with me. What do you mean by smeared out? Like a cloud?
Imagine looking at a spinning fan blade. You can't say exactly where the blade is, right?
Yeah.
It occupies a blur of probabilities.
Right.
Because the proton's location is a probability wave, there is a tiny, infinitesimal, but non-zero chance that a proton isn't just approaching the repulsive magnetic wall, but is actually already on the other side of it.
Wait, so you're telling me the particles don't actually get enough energy to climb over the wall? They just teleport through it?
They absolutely do. They tunnel through the barrier. It's a bizarre quantum loophole where the universe essentially allows the proton to cheat its way past the electrostatic repulsion, provided it gets close enough.
That is wild.
Now, the probability of any single proton tunneling through the barrier at 13 million degrees is astronomically low. We are talking about odds so small they are hard to articulate.
So if the odds are that terrible, why does the sun work?
Because of sheer volume. The core of the sun is so incomprehensibly massive, and the density is so extreme that there are literally octillions of protons colliding every tiny fraction of a second.
Ah, brute force.
Exactly. Even if the odds of tunneling are 1 in a trillion, when you have that many collisions happening, the quantum loophole is exploited millions of times a second. It happens enough times to light up the star, warm our planet, drive the weather, and sustain all life on Earth. Without quantum tunneling, the stars simply would not shine.
That is, wow. It's like flipping a coin and trying to get it to land perfectly balanced on its incredibly thin edge. The odds are practically zero.
Yeah.
But if you have a trillion coins and you dump them all out of an airplane at the exact same time, a bunch of them are going to land on their edges.
That is a brilliant way to visualize it. The universe wins the cosmic lottery simply by buying every possible ticket every single second.
Okay, that brings us perfectly to our next major theme. The sheer human ingenuity required to figure this out. Because knowing today that quantum tunneling allows stars to burn is one thing. We have the internet, we have supercomputers. But how on earth did human beings in the early 20th century figure this out? We didn't have space probes flying to the sun. We were barely flying biplanes.
Right. We transition here from the mechanics of the universe to the detective work of early modern physics. It really starts gaining traction around 1915. An American physical chemist named William Draper Harkins was the first to formalize the concept, suggesting that the fusion of light elements into heavier ones might be a source of immense energy. But the real empirical breakthrough required new tools. In 1919, an English chemist named Francis Aston invented an incredible device called the mass spectrometer.
A mass spectrometer. I hear that word on crime shows all the time.
Yeah.
But in 1919, what did this machine actually do? How do you weigh an atom? You don't just put it on a tiny little scale?
No, you use magnetism. Aston's device worked by ionizing atoms, giving them an electric charge, and then firing them through a strong magnetic field.
Okay.
The magnetic field bends the path of the flying atoms. The lighter the atom, the more its path is bent. By measuring exactly where the atoms hit a photographic plate at the end of the machine, Aston could calculate their mass with unprecedented microscopic precision. And when he did this, he made a crucial, reality-altering discovery.
Let me guess. He weighed hydrogen and he weighed helium.
He did. He found that 4 individual hydrogen atoms, when weighed separately, are slightly heavier than one single helium atom.
Ah, the missing mass, the 0.7% we talked about earlier. He found the missing change in the cosmic couch cushions.
Exactly. Aston found the mass defect. And the very next year, in 1920, the brilliant British astrophysicist Arthur Eddington put the puzzle pieces together. Eddington was one of the few people in the world who fully grasped Einstein's relatively new E=mc² equation.
Right.
He looked at Aston's missing mass, he looked at Einstein's math, and he logically deduced that stars must be giant furnaces fusing hydrogen into helium and releasing that missing mass as light and heat.
What fascinates me about Eddington is that he made this bold claim before they even had proof that stars were made mostly of hydrogen, right? Because before this, what did the scientific establishment think powered the sun? Did they think it was just like a giant lump of burning coal?
Well, some earlier scientists actually did calculate what would happen if the sun were made of coal. Yeah. It would burn out in a few thousand years. But by Eddington's time, the leading scientific theory was the contraction hypothesis, championed by giants like Lord Kelvin. This theory suggested the sun was an immense ball of gas that was slowly shrinking. As it contracted under its own gravity, it compressed the gas, releasing gravitational potential energy as heat.
Which, I mean, makes sense on paper. When you compress a gas, it gets hot.
It does. But Eddington saw the fatal flaw. He noted that if the contraction hypothesis were true, calculations showed the sun could only be a few tens of millions of years old before it would have shrunk to its current size.
Ah.
This completely contradicted the emerging geological and biological record of Earth. Geologists were finding rocks that were hundreds of millions of years old. Charles Darwin's theory of evolution required hundreds of millions of years. The sun had to be older than the rocks on Earth.
Oh, that's brilliant.
What's fascinating here is that Eddington accurately predicted stellar fusion before the actual discovery of thermonuclear energy in a lab, before quantum tunneling was even hypothesized by Hund, and before scientists universally agreed on the hydrogen composition of stars.
Just pure deduction.
Exactly. Furthermore, Eddington calculated that if a star contained just 5% hydrogen, that tiny missing mass from fusion would provide enough fuel for the star to burn brightly for billions of years, perfectly aligning with the age of the Earth. It was a triumph of pure deductive reasoning against the consensus of his day.
It's just amazing that these scientists were playing with the fundamental forces of the universe using rudimentary 1920s and 1930s technology. It's just glass tubes, magnets, and math. Eventually, they stopped just theorizing about it and started trying to do it themselves. They built early particle accelerators, right? Cyclotrons.
Yes, the desire to prove this experimentally really drove the creation of the first atom smashers. The Cavendish Laboratory in Cambridge became legendary for this. In 1932, John Cockcroft and Ernest Walton built a massive sparking particle accelerator.
Sounds like something out of Frankenstein.
It kind of looked like it, too. They were heavily inspired by George Gamow, who had taken Hund's idea of quantum tunneling and applied it to nuclear physics. Cockcroft and Walton fired protons down a tube at a piece of lithium, and successfully managed to split the lithium nucleus, producing helium. It was a massive breakthrough in artificial atomic transmutation.
But that was technically splitting the atom fission, or at least a type of it. When did they actually get two things to fuse together? I read in the notes that Ernest Lawrence, the famous American physicist, actually did it by accident in 1933.
He did. Lawrence's team at the University of California Radiation Laboratory had just invented the cyclotron, which is a circular particle accelerator. They were firing deuterons at each other.
Real quick, what is a deuteron?
Good catch. So a normal hydrogen atom's nucleus is just one single proton, but hydrogen has heavier siblings called isotopes. Deuterium is an isotope of hydrogen where the nucleus has one proton and one neutron. A deuteron is just the nucleus of a deuterium atom.
Okay, so a slightly heavier hydrogen.
Right. Lawrence's team fired these deuterons at each other. Their instruments detected energized protons and neutrons flying out of the target area. But Lawrence and his team completely misinterpreted the results.
Oh, no.
Yeah, they thought the fast-moving deuterons were just fragile, and when they crashed, they were disintegrating, just breaking apart into a proton and a neutron.
Oh, man. They missed the aha moment. They didn't realize the energy wasn't from breaking apart. It was from two deuterons fusing together and violently spitting out a leftover particle.
They completely missed it. It wasn't until the following year, in May 1934, that Mark Oliphant, Paul Hartek, and Ernest Rutherford, back at the Cavendish lab, ran an intentional, carefully measured deuterium experiment.
And they got it right.
They did. They bombarded a target with deuterons and correctly identified that they weren't breaking them apart. They were forging entirely new, heavier elements. Specifically, they discovered they were creating tritium, which is an even heavier isotope of hydrogen with two neutrons and helium-3. That 1934 experiment is widely considered the very first definitive experimental demonstration of nuclear fusion on Earth.
And once they cracked that code, once they proved the fire of the stars could be lit on Earth, the world changed forever. Which brings us to the next chapter of our story. Because humans, being humans, the moment we realized we could release millions of times more energy than standard chemical reactions, our first instinct wasn't to build a city-powering utopia. We decided to build a bomb.
The transition from pure academic curiosity to terrifying military application was incredibly rapid. This was driven entirely by the existential urgency of World War II and the sprawling apparatus of the Manhattan Project.
Right.
Fission-splitting heavy atoms like uranium and plutonium was weaponized first. The atomic bombs dropped on Japan were fission devices. But the visionary physicists of the era always knew that fusion had vastly more potential for destruction.
Because the energy release per gram of fuel is just so much higher.
Exactly. In 1941, during the early days of atomic research, Enrico Fermi and Edward Teller had a pivotal conversation. They knew fusion required the astronomical temperatures of the sun, millions of degrees. Fermi casually suggested that maybe, just maybe, the immense heat and pressure generated by an exploding fission bomb could be used as a macroscopic spark plug to ignite a fusion reaction.
Let's just pause and appreciate the madness of that thought. How do we light this fire? Well, what if we use an atomic bomb as a match?
It sounds like dark science fiction, but it was physically sound. To simulate the extreme temperatures and pressures to see if it would work, Los Alamos scientists like John von Neumann and Teller used ENIAC.
The early computer.
Yes. ENIAC was one of the very first electronic general-purpose computers in the world. They used it to run the mind-numbingly complex thermonuclear hydrodynamic math. And the computer told them it would work. In 1952, the United States detonated the Ivy Mike test. This was the first true thermonuclear device using what is now known as the Teller-Ulam two-stage design.
A two-stage design. So stage 1 is the fission atomic bomb, stage 2 is the fusion fuel, and the yield on Ivy Mike.
Over 10 megatons. To put that in perspective, a megaton is the explosive equivalent of 1 million tons of TNT. Ivy Mike was roughly 700 times more powerful than the fission bomb dropped on Hiroshima. It completely obliterated the Pacific island it was placed on. The Soviet Union followed shortly after, testing their own two-stage thermonuclear design, the RDS-37, in 1955.
But looking through the historical notes here, Ivy Mike wasn't really a usable weapon, right? It was like the size of a factory.
Correct. Ivy Mike used liquid deuterium for its fusion fuel. To keep deuterium liquid, you have to cool it to near absolute zero. So the bomb was actually a massive multi-story building filled with heavy cryogenic refrigeration equipment.
So you're not dropping that from a plane.
You couldn't drop it out of an airplane or put it on a missile. It was a proof of concept science experiment.
Which brings us to 1954 and a test called Castle Bravo. And looking at the facts here, it sounds like this is where the math went catastrophically, terrifyingly wrong, because they tried to make the bomb portable.
Yes, Castle Bravo is a profoundly sobering historical event. To solve the refrigeration problem, the weapons designers created a dry bomb. Instead of liquid deuterium, they used a solid, room-temperature compound called lithium deuteride.
Okay, so you have solid fuel, looks like a powder or a salt, much easier to pack into a metal casing and drop out of a bomber. But how does lithium help you make fusion?
It was an incredibly clever piece of nuclear engineering. The designers knew that when the primary fission spark plug went off, it wouldn't just create heat, it would release a massive blinding flood of high-energy neutrons. They specifically used the isotope lithium-6 in the fuel compound.
Okay.
When a fast-moving neutron smashes into a lithium-6 atom, the lithium atom shatters, and it breeds tritium.
Tritium, the heavy hydrogen with two neutrons.
Yeah.
The perfect, highly combustible fusion fuel.
Exactly. The bomb basically manufactures its own high-grade fusion fuel inside the casing milliseconds before the immense heat and pressure caused that fuel to detonate. It was elegant, but there's a fatal flaw in their understanding of the material.
Okay, what was the catch? What did they miss?
The lithium deuteride compound they manufactured wasn't pure lithium-6. Isolating pure isotopes is extremely expensive and difficult, so the fuel was a mix. It contained about 40% lithium-6 and 60% lithium-7, which is a slightly heavier, much more common isotope.
Right.
The physicists at the time believed lithium-7 was essentially inert in this thermonuclear scenario. They thought it would just act like dead weight, a spectator to the reaction.
So they basically miscalculated the chemistry of the bomb? They thought 60% of the fuel was just filler.
Well, it wasn't a chemistry error. It was an error in nuclear cross-section mathematics.
Hold on, cross-section. I've seen this term a few times in the physics notes. When you say cross-section, I'm picturing cutting an apple in half and looking at the inside. What does that mean in nuclear physics? Is it like the size of the target the neutron is trying to hit?
That is an excellent analogy, yes. A nuclear cross-section is essentially a measure of the probability that a specific reaction will occur when a particle, like a neutron, hits a specific nucleus. Think of it as the size of the bullseye on a dartboard. A large cross-section means it's a huge bullseye, very likely to interact. A small cross-section means a tiny bullseye.
Got it.
The designers looked at the cross-section of lithium-7 and concluded it wouldn't interact with the neutrons. What they didn't realize, and what their math failed to predict, was that at extremely high neutron energies, specifically when the neutrons are traveling with energy above 5 mil lithium-7 does not remain inert, its cross-section changes drastically.
All right.
It actually undergoes fission. It absorbs a fast-moving neutron, becomes highly unstable, and violently splits apart, and when it splits, it produces an alpha particle, an extra neutron, and crucially, an immense amount of extra tritium.
Oh, wow. So the 60% of the bomb that they thought was inert filler just woke up. It didn't just sit there. It dumped massive amounts of extra, unexpected fuel directly into the thermonuclear fire.
Yes. Calmly looking at the historical facts and measurements from that day, the result of that miscalculation was just horrifying. The designers predicted Castle Bravo would yield about 6 megatons of explosive force. The actual explosion yielded 15 megatons. It was 150% more powerful than they predicted.
That is insane.
It remains the most powerful nuclear device ever detonated by the United States. The explosion was so incomprehensibly powerful, it vaporized the testing islands, created a crater over a mile wide, and pushed a mushroom cloud 130,000 feet into the stratosphere.
Wow.
Because the yield was so unexpectedly huge, it caused catastrophic, widespread radioactive fallout that coated thousands of square miles of the Pacific. It affected nearby inhabited atolls, forcing the permanent evacuation of indigenous populations, and severely poisoned the crew of a Japanese fishing boat called the Lucky Dragon No. 5, who were well outside the expected danger zone.
It's just a staggering tragedy, and it really emphasizes the sheer scale of what we were dealing with here. We aren't just boiling water. We're playing with the exact forces that build and destroy galaxies.
We really are.
Which actually bridges us perfectly to our next topic. Because the Cold War weapons showed we could create uncontrolled fusion, a momentary terrifying flash.
Yeah.
But if we ever want to control this, if we want to build a reactor that actually powers humanity, we have to look at how the universe does it natively. We have to look at the star stuff.
The universe is the ultimate original fusion laboratory. And it all started incredibly early in the timeline of reality. We are talking about Big Bang nucleosynthesis.
Right after the universe was born.
Exactly. From about 10 seconds to roughly 20 minutes after the Big Bang, the entire universe was essentially one giant, omnipresent fusion reactor. In the very first seconds, it was too hot even for fusion. Protons and neutrons couldn't stick together.
They're just moving too fast.
Exactly. But as the universe expanded, it cooled. It cooled down from over 100 keV of energy to about 1 keV. This specific temperature band was the perfect Goldilocks zone for protons and neutrons to start slamming together and sticking.
So in that tiny 20-minute window, the universe forged the very first elements.
Yes. It forged immense amounts of deuterium, tritium, and helium, along with a tiny microscopic sprinkling of slightly heavier elements like lithium, beryllium, and boron. It's a stunning fact of cosmology that almost all of the helium currently existing in the entire universe was created in those first 20 minutes of existence.
That is wild. The universe just cooked up a massive batch of helium and then stopped. Why did it stop after 20 minutes?
Because the universe was expanding incredibly rapidly. As it expanded, the density of the particles dropped and the temperature plummeted below that 1 keV threshold. The particles simply weren't moving fast enough or packed tightly enough to overcome the Coulomb barrier anymore. The cosmic reactor just shut down.
Okay, but obviously that isn't the end of the story. The universe isn't just made of hydrogen and helium. Where did all the other elements come from? The carbon in my body, the oxygen I'm breathing, the gold in my ring.
That brings us to stellar nucleosynthesis. Hundreds of millions of years after the Big Bang, vast clouds of that primordial hydrogen gas began to collapse under their own gravity. As the gas compressed, it heated up again until the core of these massive clouds reached millions of degrees. The fusion reactor restarted. Stars were born.
Okay, so round 2 of fusion.
Yes. In stars the size of our sun, the primary engine is the proton chain reaction, which we discussed earlier, relying heavily on quantum tunneling to slowly fuse hydrogen into helium. But the universe has much bigger engines. In stars much heavier than the sun, the gravity is crushing. The core pressure and temperature are significantly higher. They don't use the slow proton chain. They use something called the CNO cycle.
CNO, let me guess, carbon, nitrogen, oxygen.
Exactly. In these massive stars, carbon, nitrogen, and oxygen act as catalysts.
Okay, refresh my memory on catalysts.
A catalyst is something that speeds up a reaction without being consumed by it. These heavier elements essentially capture protons, shuffle them around through a series of rapid radioactive decays, and spit out a helium nucleus, returning to their original state to do it all again. The CNO cycle fuses hydrogen into helium exponentially faster than our sun does, which is why massive stars live very short, incredibly bright lives.
Makes sense. They burn through their fuel way faster.
And if we pause here and connect this to the bigger picture, the listener really needs to understand the profound intimacy of this process. Every single atom of carbon in your DNA, every atom of oxygen in your lungs, the nitrogen in your muscles, and the iron in your blood, none of it was created in the Big Bang.
Oh, wow.
It was forged in the unimaginably hot core of a massive star that lived, exhausted its fuel, and exploded in a supernova billions of years before the Earth even existed. We are, quite literally, as Carl Sagan famously said, made of star stuff.
I will never, ever get tired of hearing that. It is the most poetic truth in all of science. But, the universe doesn't just stop at normal, shiny stars, right?
Yeah.
The notes mention some truly wild cosmic phenomena under the heading of extreme astrophysics. We're talking about things going bump in the night on a cosmic scale.
Yes, fusion isn't limited to the centers of main sequence stars. It happens in some of the most extreme, violent environments imaginable. Take brown dwarfs, for example.
I heard them called failed stars.
That is the common term, yeah. A brown dwarf is a ball of gas heavier than Jupiter, but not quite massive enough to generate the core pressure needed to sustain continuous hydrogen fusion. However, during their formation, they are massive enough to fuse deuterium and lithium. Because deuterium fuses at a lower temperature than normal hydrogen, they manage to ignite for a short period, maybe a few million years, before sputtering out and slowly cooling into darkness.
Like a cold car engine trying to turn over, firing a few times, and then just dying. What about white dwarfs?
White dwarfs are the ultra-dense dead remnants of stars like our sun. They are mostly made of carbon and oxygen packed into a sphere roughly the size of the Earth. Normally, they just sit there, slowly cooling over trillions of years. But if a white dwarf is in a binary star system, orbiting very close to a normal companion star, its immense gravity can start siphoning gas off the companion.
Oh, like a vampire star.
Exactly. As it steals this matter, the white dwarf gets heavier and heavier. As it gains mass, its internal pressure skyrockets. It approaches a critical threshold called the Chandrasekhar limit, which is exactly 1.44 times the mass of our sun. Just before it hits that limit, the temperature and density inside the dead star becomes so extreme that a runaway carbon-burning fusion reaction ignites.
Wait, runaway, so it doesn't just wake up and start shining like a normal star again?
No, the material in a white dwarf is degenerate matter. It doesn't expand when it gets hot like a normal gas does, so the temperature skyrockets, but the star doesn't puff out to cool down. The fusion reaction spreads through the entire Earth-sized star in a fraction of a second. It completely obliterates the star in a colossal explosion known as a Type Ia supernova. Every single atom of carbon and oxygen in the star fuses almost simultaneously.
That is absolutely terrifying. A zombie star waking up just to blow itself to pieces.
Yeah.
But the notes here also talk about neutron stars
Yeah.
and black holes. Here's where it gets really interesting for me. You're telling me fusion can happen near a black hole. I thought black holes just ate everything.
They do, but it's a very messy process. First, let's look at neutron stars, which are even denser than white dwarfs. Imagine the mass of the sun crushed into a sphere the size of Manhattan. They can also accrete gas from a companion star. The stolen hydrogen and helium build up on the incredibly dense, hard surface of the neutron star.
Okay.
The gravity is so strong that the gas is compressed into a flat, ultra-dense ocean. Eventually, the pressure at the bottom of this ocean becomes so high that a thermonuclear wave ignites and burns across the entire surface of the star in about 1 second. We observe these as massive bursts of X-rays deep in space.
An ocean of fire on a city-sized star? Unreal.
But yes, the black hole accretion disks are arguably the most extreme fusion environments in the universe. As matter swirls down the impossibly steep gravity well of a black hole, it doesn't fall straight in. It forms a flat, spinning disk like water circling a drain.
Right, the accretion disk.
The friction between the particles in this accretion disk, whipping around at near the speed of light, is so intense that the gas heats up to billions of degrees. Calculations show that in the inner edges of these disks, especially around lower-mass stellar black holes, the temperatures and densities are so astronomically high that it triggers spontaneous fusion.
Wow.
And because it's so hot, it's not just fusing hydrogen. We're talking about fusing heavy elements like silicon and selenium right on the precipice of the event horizon, right before the matter falls out of the observable universe forever.
So fusion is happening in the swirling, superheated vortex outside a black hole. It's just mind-bending to visualize. But there's a common denominator in all of these cosmic examples, right? The universe uses extreme, mind-crushing gravity to confine that plasma, to squeeze it until the atoms have absolutely nowhere to go but into each other.
That's the secret to stellar fusion, yes.
But on Earth, we do not have a black hole, and we do not have the gravity of a star. We are standing on a relatively tiny rock. So how do we hold something that is 10 to 100 times hotter than the center of the sun without it instantly blowing apart or, melting our machines?
That is the trillion-dollar engineering question. How do you hold a star in a jar when the star wants to vaporize the jar? And this brings us to the terrestrial confinement methods. Because we don't have gravity to squeeze our fuel, we are playing a highly complex game defined by a mathematical principle called the Lawson criterion.
The Lawson criterion. That sounds like the title of a Jason Bourne movie. What exactly is it?
It was formulated by John Lawson in the 1950s. It is essentially the required triple product of fusion. To get a self-sustaining fusion reaction, a state we call ignition, where the energy produced by the fusion keeps the plasma hot enough to continue fusing without outside help,
Yeah.
you need 3 variables perfectly balanced. You need temperature, you need density, and you need confinement time.
Okay, so how hot the fuel is, how tightly packed together the atoms are, and how long you can actually hold them in that state before they escape.
Precisely. It is a strict mathematical trade-off, because we cannot even come close to replicating the density at the center of a star. In fact, the plasma inside our best reactors is actually about 1 million times less dense than the air you are breathing right now, and it's virtually a vacuum. We have to drastically overcompensate with the other 2 variables.
Make them hotter and hold them longer.
Exactly. We have to push the temperature incredibly high. Not 14 million degrees like the sun, but 100 million or even 150 million degrees Kelvin, and we have to confine it for a significant amount of time.
I just need to pause on that.
Yeah.
150 million degrees. If I put something that hot inside a physical metal box, it doesn't matter what the metal is made of, titanium, tungsten, it would instantly vaporize. So what on earth do you put it in?
You are absolutely right. No physical material in the universe can withstand that temperature. That is why we can't use a physical box. We have to build an invisible box. The leading, most mature method for doing this is called magnetic confinement.
Magnetic confinement.
Okay,
Cool.
because the fuel at 150 million degrees is a plasma, a distinct state of matter where the electrons have been ripped away from the nuclei, creating a swirling soup of electrically charged ions and electrons. It responds strongly to magnetic fields.
Right, because they're charged.
Yes, so we use colossal, supercooled electromagnets to trap the charged particles in a vacuum chamber. We create magnetic force fields that guide the plasma, keeping it suspended in midair so that it never, ever touches the physical walls of the machine.
And when I look up fusion reactors online, the pictures are usually these massive circular metal machines. The most famous of these magnetic boxes are tokamaks and stellarators, right? Tokamaks are the ones shaped like a giant donut.
Yes, a toroidal geometry is the technical term. The tokamak was originally designed by Soviet physicists in the 1950s. It uses powerful magnetic coils wrapped around the donut, plus an electrical current driven directly through the plasma itself to twist the magnetic field lines and cage the particles.
Okay, and a stellarator.
A stellarator does the same thing, but instead of driving a current through the plasma, it uses incredibly complex, computer-designed, twisted magnetic coils that look like a piece of modern art to create the cage. It's much harder to build, but theoretically more stable.
And are these actually working?
We have made incredible, tangible progress with these magnetic bottles. The JET reactor in the UK, the Joint European Torus, set a massive world record in late 2023, producing 69 megajoules of fusion energy over 5 seconds. And just recently, France's West reactor maintained a superheated plasma at roughly 50 million degrees for a record 6 minutes.
6 minutes. That sounds like an eternity when you're essentially holding a piece of the sun in a magnetic net. But magnetic confinement isn't the only horse in this race. The notes heavily feature an entirely different approach called inertial confinement. This doesn't use magnets at all. This involves lasers, right?
Yes, and this is where the National Ignition Facility, or NIF, located at the Lawrence Livermore National Laboratory in California, comes into the spotlight. If magnetic confinement is like trying to keep a fire burning steadily in an invisible fireplace, inertial confinement is about creating tiny, microscopic, incredibly violent explosions.
Oh, wow.
They do not use a continuous magnetic donut. Instead, they take a tiny, perfectly spherical pellet of fusion fuel no bigger than a peppercorn, and they fire 192 of the world's most powerful lasers at it simultaneously.
So they just zap this tiny peppercorn from all sides with massive lasers.
Not exactly, and the mechanism here is fascinating. In the NIF design, the lasers don't actually hit the fuel pellet directly. The peppercorn of fuel is suspended inside a tiny cylinder made of pure gold called a Hall round.
A gold cylinder. Why gold?
Because of how it interacts with the lasers. The 192 lasers enter through holes in the ends of the cylinder and strike the inside walls of the gold. The gold absorbs the laser energy and instantly vaporizes into a plasma, which emits a blinding, incredibly intense bath of X-rays. It is this X-ray oven that actually heats the outer shell of the tiny fuel pellet inside.
Okay, so the lasers make X-rays, the X-rays hit the pellet. What happens to the pellet?
The outer surface of the pellet absorbs the X-rays and explodes outward at hundreds of kilometers per second. Now, Newton's third law states that every action has an equal and opposite reaction. Because the outer shell explodes outward like the exhaust of a rocket, the inner core of the fuel is driven violently inward. It implodes.
It crushes itself.
Exactly. The fuel inside is compressed so explosively, so fast, that it reaches fusion temperatures and densities, hundreds of billions of atmospheres of pressure, before it even has time to realize what is happening and blow apart. It is called inertial confinement because the sheer physical inertia of the imploding mass holds the plasma together just long enough, a tiny fraction of a billionth of a second, for the fusion reactions to ignite.
And in December 2022, NIF actually hit a historic paradigm-shifting milestone. I remember the whole world was talking about it. The notes say they achieved ignition. They got 3.15 megajoules of fusion energy out from 2.05 megajoules of laser energy put into the target. That's scientific break-even. They proved you can get more energy out than you put in.
It was a monumental victory for physics, unequivocally. It proved that laboratory ignition is possible. But as with all things fusion, we have to analyze it with a clear, critical head.
Right, there's always a catch.
The NIF breakthrough proved that the target saw a net energy gain. The fuel produced more energy than the X-rays delivered to it. However, the immense caveat is the lasers themselves. To generate those highly precise 2.05 megajoules of laser light, The NIF facility had to pull roughly 300 megajoules of electricity from the California national grid.
Oh, wow. That's a
Yeah.
huge difference.
Yeah, the laser architecture is based on 1990s technology. It is highly inefficient. So while the fundamental physics of the exploding pellet finally worked flawlessly, the engineering of building a laser facility that can actually power a city is still a marathon away.
Okay, so we have massive stadium-sized laser facilities. We have giant multi-billion-dollar magnetic donuts. But what about this next bullet point in the outline? Electrostatic confinement, fusers. It explicitly says amateurs and high schoolers are building these in their garages. You're telling me people are building functional nuclear fusion reactors next to their lawnmowers in their basements? That is simultaneously the coolest and most terrifying thing I've heard today.
It is entirely true and surprisingly perfectly safe, relatively speaking. A fuser is a device that uses inertial electrostatic confinement. Instead of complex superconducting magnets or multi-billion-dollar lasers, it simply uses high voltage.
How does that work?
Imagine two spherical wire cages, one inside the other, sitting inside a vacuum chamber. You apply a massive negative electrical voltage to the inner wire cage, and you pump a tiny bit of deuterium gas into the chamber. The voltage strips the electrons off the deuterium, creating positively charged ions. Because opposites attract, those positive ions are pulled violently, accelerating toward the negative inner cage.
Okay, so they are flying toward the center. What happens when they get there?
Well, most of them are unlucky. They just crash into the metal wires of the inner cage, heat up the metal, and lose all their kinetic energy. But a few of them fly right through the empty gaps between the wires. They sail into the very center of the cage from all directions, meet in the middle, collide head-on at immense speeds, and fuse.
So it's like a microscopic demolition derby in a vacuum chamber.
Exactly, and it genuinely works. It creates true nuclear fusion, and you can use radiation detectors to pick up the neutrons flying out to prove it. High school students have won science fairs with them.
That is incredible.
But there is a massive catch. Because the vast majority of the ions just hit the physical wire grid and lose their energy, the device suffers from massive conduction losses. A fuser will always perpetually consume vastly more electricity from the wall outlet than it produces in fusion energy. It is a fantastic educational tool. It is a great, cheap way to generate neutrons for medical research, but it will never, ever power a city.
All right, so we've covered the machines, the tokamaks, the stellarators, the lasers, the basement wire cages.
Yeah.
But what exactly are we putting into them? Which brings us to Section 6, the fuel in the future. Because obviously, not all fusion is created equal, right? You can't just take a bucket of regular tap water from the sink and throw it into a tokamak.
No, you cannot. Finding the optimal fuel for these early reactors is an intricate, agonizing balancing act between the laws of physics and the limits of material engineering. The standard fuel for almost all major near-term fusion power projects today is a mixture called DT deuterium and tritium.
We mentioned these earlier. Both are heavier isotopes of hydrogen. Deuterium has 1 neutron, tritium has 2.
Right, DT is the fuel of choice because, mathematically speaking, it is the easiest to ignite. Its reaction rate peaks at the lowest temperature compared to any other fuel combination, around 70 keV, which translates to roughly 800 million Kelvin.
Still insanely hot.
Yes, still insanely hot, but it is achievable. Furthermore, DT has the highest nuclear cross-section, it has the biggest bullseye, the particles are highly likely to fuse when they collide. When a deuterium and a tritium atom fuse, they produce a stable helium-4 nucleus, the doubly magic ash we discussed, and one single, extremely fast-moving neutron.
The outline notes that this neutron carries 14.1 MeV of kinetic energy. Sounds great if you're trying to extract energy to boil water and make power. But the notes also explicitly list the neutron problem. Why is a high-energy neutron considered a massive headache for the engineers?
Because neutrons, by definition, have no electrical charge. Our brilliant magnetic fields in the tokamak can trap the positively charged deuterium and tritium ions perfectly. The magnetic cage is watertight for charged particles, but the magnetic field has absolutely zero effect on a neutral particle.
No, I see.
The exact millisecond that neutron is born in the fusion reaction, it ignores the magnetic field entirely, flies straight out of the plasma bottle at a massive fraction of the speed of light, and violently smashes into the physical metal walls of the reactor chamber.
So it hits the physical wall.
And at 14.1 MeV, it hits it like a microscopic cannonball. Now, this kinetic energy is actually how we plan to generate electricity. The billions of neutrons impact the inner blanket of the reactor. Their kinetic energy turns into heat, We run a coolant like liquid lithium or water behind the wall to capture that heat, make steam, and turn a turbine.
Sounds like standard power plant stuff so far.
It is, but that continuous, unrelenting bombardment of high-energy neutrons structurally degrades the metal over time. It knocks atoms out of their crystal lattice, it causes severe radiation damage, making the steel brittle, swollen, and crucially highly radioactive. To make a commercial power plant viable, we have to design entirely new, exotic alloys and ceramic materials just to survive the interior of a DT fusion plant without needing to be replaced every 6 months.
Which sounds like a material science nightmare. Is there a fuel that just doesn't produce neutrons? Like, the neutrons are the problem. Can we just use something else?
Yes, there's an entire class of theoretical reactions called antitronic fusion, and the absolute holy grail in this category is fusing single protons, just regular, everyday hydrogen nuclei, with an isotope of boron called boron-11. In physics, we call it PB11.
Okay, proton and boron.
When a proton and a boron-11 nucleus fuse, they momentarily create a highly unstable carbon-12 nucleus, but it doesn't stay carbon. It almost immediately shatters into exactly 3 alpha particles. Alpha particles are just helium nuclei.
So 3 pieces of completely harmless helium and no neutrons.
Exactly, 0 neutrons. 100% of the energy from the reaction is carried by the positively charged helium particles, which means you wouldn't even need to boil water to make steam, which is a 19th century technology anyway.
Right.
Because the products are electrically charged, you could potentially use the moving magnetic fields of the escaping helium to induce a current in coils, generating electricity directly with incredible efficiency, and the reactor walls would never become radioactive.
That sounds like absolute science fiction in the best way possible. Clean, direct electricity, no radioactive waste, no brittle walls. Why aren't all the billion-dollar startups just doing that?
Because nature is stubborn, and we return to the Lawson criterion. PB11 requires temperatures nearly 10 times higher than DT fusion to ignite. We are talking well over 1 billion degrees. And when you heat a plasma to 1 billion degrees, you run headfirst into the ultimate buzzkill of advanced fusion fuels: Bremsstrahlung radiation.
Bremsstrahlung. That sounds German.
It is. It translates directly to breaking radiation. In any plasma, you have positively charged ions and negatively charged electrons zipping around at tremendous speeds. When a fast-moving electron zips past a highly charged heavy ion like boron, the ion's strong electric field tugs on the electron. It bends the electron's path and rapidly slows it down.
Like hitting the brakes.
Exactly. In physics, whenever a charged particle accelerates or decelerates when it hits the brakes, it must conserve energy by emitting electromagnetic radiation. In a plasma this hot, that radiation is emitted in the form of highly energetic X-rays.
Okay, so X-rays are shooting out of the plasma. Why is that a buzzkill? Don't stars emit X-rays?
Stars do, but here is the critical difference between a star and a machine: optical thickness. In the core of a star, the plasma is incredibly dense. It is optically thick. When an X-ray is emitted, it immediately bounces into another atom, another, and another. The energy stays trapped inside the star, keeping the core hot. But in our terrestrial reactors, remember, the plasma is a near vacuum. It is optically thin. The X-rays act like light passing through clear glass. They pass right out of the magnetic bottle, hit the cold metal walls, and are absorbed. The X-rays carry vital heat energy away from the fuel.
Oh, they bleed the heat.
Exactly.
Yeah.
It's like trying to boil a pot of water on a stove, but the pot has 100 tiny holes leaking the hot water out. For DT fusion, the fusion energy produced is vastly greater than the energy bled away by Bremsstrahlung X-rays. The fire outpaces the cooling. But for PB11, because boron has a much higher electrical charge, it has 5 protons, the Bremsstrahlung losses are immense. The X-rays bleed heat away almost exactly as fast as the fusion reaction generates it, making it incredibly difficult, perhaps mathematically impossible in a standard tokamak, to ignite the plasma without it cooling itself down.
Wow. The universe really, really does not want to give up this secret easily. Every time we solve one problem, physics throws up a wall. Okay, so DT has neutrons that wreck the reactor walls. PB11 bleeds all its heat through X-rays. Are there any truly outside-the-box ideas? The outline mentions some alternative fringe concepts, like what is muon-catalyzed fusion?
That is one of the most fascinating pieces of theoretical physics of the 20th century. Muons are subatomic particles that act exactly like electrons in almost every way. They have a negative charge, they spin, but they are about 207 times heavier than an electron. In the 1980s, physicists Stephen Jones and others explored the idea of replacing the electrons in a hydrogen atom with these heavy muons. Because the muon is 200 times heavier, Quantum mechanics dictates that its orbit is 200 times closer to the nucleus.
So it pulls the whole atom much, much tighter together.
Exactly. It physically shrinks the hydrogen atom by a factor of 200. Because the atoms are so incredibly small, they don't repel each other until they are vastly closer together. This allows the nuclei to undergo quantum tunneling and fuse at literal room temperature. It is a genuine, mathematically sound mechanism for cold fusion.
Wait, room temperature fusion. That solves the temperature problem. That solves the plasma problem. Why isn't this the headline of every newspaper?
Because of the harsh reality of thermodynamics,
Right.
net energy production has proven impossible so far. First, muons don't exist naturally on Earth for long. They rain down from cosmic rays. But to get enough of them, you have to generate them using massive particle accelerators, which consume immense amounts of electricity.
So it takes energy to make them.
Furthermore, a muon is unstable. It only lives for 2.2 microseconds before decaying into an electron and neutrinos. But the fatal flaw is what we call alpha sticking. After the muon catalyzes the fusion of deuterium and tritium, an alpha particle helium is created. About 1% of the time, the negatively charged muon gets stuck to the positively charged helium particle. It is captured and taken out of the game. It can't go catalyze another reaction.
So you constantly have to manufacture more of them.
Yes, and it simply costs far more energy to manufacture the muons than you get back from the 100 or so fusions a single muon can catalyze before it gets stuck or dies.
Okay, what about pyroelectric fusion? The notes say this happened at UCLA.
This was a brilliant, highly policized 2005 experiment at UCLA. They used a pyroelectric crystal. These are unique materials that generate a massive electric field when you change their temperature. They put the crystal in a vacuum chamber, heated it up slightly, and attached a tiny tungsten needle to it. The heat caused the crystal to generate an astonishing electric field of about 25 gigavolts per meter at the tip of the needle. This field literally ripped deuterium molecules apart, ionized them, and shot the deuterons like a microscopic particle accelerator into an erbium target, causing them to fuse.
So wait, they literally built a desktop fusion reactor.
They did, but again, strictly as a neutron generator for research, it requires vastly more energy to heat the crystal and run the equipment than the microscopic amount of fusion energy it outputs. It is a brilliant piece of physics, but it is not a power plant design.
All right, what about this last fringe idea? Project Pacer. 1970s.
Project Pacer. This was investigated heavily by the Los Alamos National Laboratory. It is, without a doubt, the most brute force, terrifyingly pragmatic approach to fusion energy ever conceived.
I'm listening.
The logic was simple. We struggle to contain plasmas in magnets. We struggle with lasers. But we know absolutely, flawlessly, how to make massive amounts of fusion energy using hydrogen bombs. So the idea was simply to excavate a colossal underground cavern, perhaps a massive salt dome, fill the cavern with water or steam, and then drop a small 50-kiloton thermonuclear bomb into the cavern and detonate it. You detonate the bomb, the explosion superheats the steam, you siphon off some of that high-pressure radioactive steam, run it through a heat exchanger to boil clean water, turn a turbine, and make electricity. Then a few hours later, when the pressure drops, you drop another hydrogen bomb into the hole.
Wait, you're just dropping literal, actual hydrogen bombs in a cave twice a day to boil water. That is absurd.
From a purely technological standpoint, it is entirely found. In fact, it is the only fusion power system that humanity could theoretically build tomorrow morning using existing off-the-shelf technology.
Oh.
However, the economics of manufacturing tens of thousands of thermonuclear weapons every year just to run power plants is staggering. And more importantly, the geopolitics and security nightmare of having a continuous civilian industrial supply line of hydrogen bombs makes it entirely, permanently unfeasible.
Yeah, I don't think the local neighborhood zoning board is going to approve the daily H-bomb detonations. It's a little loud. So, setting aside the underground bombs, what does this all mean for us today? Because when I read the news, we have these massive international government projects like ITER being built in France, a machine that weighs as much as an aircraft carrier and is taking decades to build. But recently, we also have billions of dollars pouring into private startups, companies with names like Commonwealth Fusion Systems, Helion Energy, TAE, Zap Energy. Where do we actually stand in the real world right now?
We stand at a profound, pivotal transition point in human history. For decades, fusion was strictly the domain of governmental scientific research. The running joke in the physics community was always, fusion is 30 years away, and it always will be. But the recent influx of private venture capital, We saw over $2.6 billion invested in private fusion in 2021 alone, has fundamentally shifted the landscape.
So private money is speeding it up.
Companies are no longer just trying to prove the basic physics. They are taking the proven physics from the national labs and applying cutting-edge modern technology that didn't exist 10 years ago.
What kind of technology?
For example, Commonwealth Fusion Systems, spun out of MIT, is using novel high-temperature superconducting tape to build magnets that are vastly stronger than anything used in older reactors. Stronger magnets mean you can build a tokamak that is 10 times smaller and cheaper, but achieves the same plasma pressure.
Okay, that makes sense.
Helion Energy is trying an entirely different approach, attempting to merge plasma rings to fuse deuterium and helium-3 and trying to capture the energy directly as electricity using magnetic induction, bypassing the steam turbine entirely. Zap Energy is using something called the Z-pinch method, using the plasma's own internal magnetic field to collapse it, eliminating the need for giant external magnetic coils.
Wow.
We're decisively moving from the era of can we make the physics of a star work in a lab? To can we engineer a machine that is reliable, robust, and actually makes economic sense on the power grid?
It's the transition from the pristine science lab to the dirty, practical commercial grid.
Precisely. And while the engineering challenges of neutron bombardment, tritium breeding, because tritium has a half-life of 12 years, we essentially have to manufacture it inside the reactor. And plasma stability are still immense. The collective weight of human ingenuity is currently tackling them from a dozen different angles simultaneously.
Which really brings us to the end of our journey today. When you look at the whole arc of this, from Arthur Eddington looking up at the sky in 1920 and simply deducing the secret of the stars with pure logic, to the destructive, terrible force of the Cold War weaponization, to 192 lasers firing at a peppercorn in California and giant magnetic donuts in France. Humanity is painstakingly, stubbornly inching toward harnessing the fundamental power of the cosmos.
It's a beautiful way to sum it up.
But if you are listening to this right now, as a learner, as a citizen of Earth, you might be asking, why does this matter to me? Why should I care about plasma physics and magnetic confinement?
It's a vital question.
Because commercial fusion represents the absolute holy grail of human civilization. We are talking about baseload energy power that doesn't care if the sun is shining, or if the wind is blowing, or if there is a drought. It produces zero carbon emissions, and it is fueled by isotopes of hydrogen that we can literally extract from the water in our oceans. It is a virtually limitless energy source. It is a technology that could completely rewrite our approach to combating climate change while simultaneously elevating global living standards by providing abundant, cheap power to the entire world.
It is the ultimate decoupling of human energy production from environmental destruction. It is the final step in our mastery of fire. But before we sign off, I want to leave you, the listener, with one final, perhaps slightly provocative thought to ponder.
Oh, I'm ready.
We talked earlier about how black holes can act as the ultimate cosmic fusion engines, using the friction in their accretion disks to fuse incredibly heavy elements like silicon right on the edge of the event horizon. If humanity eventually masters DT fusion in the next few decades, and then perhaps proton-boron fusion a century later, it raises an incredible question about the deep future. Could a highly advanced future civilization, perhaps what we would call a Kardashev Type 2 civilization, artificially create micro-black holes and harness their accretion disks?
Wait, really?
If they could mathematically stabilize a tiny black hole, they wouldn't even need specific isotopes like deuterium or boron. The gravity and friction would be so intense they could throw literal garbage, dirt, or asteroid rock into the accretion disk, fuse it into heavier elements, and harvest the radiant pure energy.
That is insane.
It sounds entirely like science fiction, but the math of quantum tunneling and E equals mc squared that we discussed today dictates that the universe absolutely definitively allows it.
That is a staggering thought to end on, using a microscopic black hole as the ultimate galactic recycling bin. Thank you so much for joining us on this deep dive into the star stuff that powers our universe. Stay curious, keep looking up, and we'll see you next time.
Thank you for listening.